So in this video what we're going to do is look at graphing motion. So this is GCSE level and to do with forces and motion. Now it's a little bit difficult to show this in a video how to graph up, but we'll just see how we go. So in a graph, 2D graph, we've got two axes. You've got to label your axis with the quantity. In this case it's going to be distance with its unit and separated with a division mark. And on the x-axis we've got time in seconds. Really that should be a division mark there rather than in brackets. So this is just showing you a student who's put it in brackets, and really we want a division sign in there. Then the next thing to do is to decide on the scale that your graph is going to be. So the x-axis here on time goes from 0 to 28. Now first thing to do is to look with the scale is to look how many squares, count how many squares do you have on your graph paper. So each of these large boxes is made of 5 small boxes, and we've got 1, 2, 3, 4, 5, 6, 7, 8. So that means we've got 40 boxes. We've got 8 times 5, 40 small boxes. So that means that we can, if we wanted to, we could, which is what's been done here, we can say that each small box is worth 1 second. And we've got enough boxes to cover 28 because that 40 is bigger than the 28. We can do that. Now if we had say 60 small squares, then we could do the same, but we'd be wasting a lot of graph paper. So we would be able then to say, well, 2 small boxes is equal to 1 second, and we'd be able to spread our graph out a bit more along the width of the graph paper. So you've got to adjust your scale accordingly to the size of the graph paper. If we have a look at the y-axis here, that goes from a minimum of 0. It doesn't go from 0 to 0. The maximum is 15, right? So here we can again count how many squares do we have. Well, we've got 5 per large square. We've got 1, 2, 3, 4, 5, 6, 7, 8 again. So that means we've again got 40 small squares on the y-axis to play with. Now 40 is a lot more than 15. So on this one, we're not saying that we've got just 1 little square per meter. We're using 2 little squares per meter. So this will be 1 meter, 2 little squares. Then it'll be 2 meters for 4 little squares, 3 meters for 6 little squares, 4 meters for 8 little squares, and 5 meters for 10 little squares. So we can see that then this scale is more spread out, so to speak, than the x-axis, and that's to use the whole amount of paper. If we just squashed it down and we put a 5 here, 10, 15, then the graph would only come up to here, and it would be wasting all of this graph paper. And that's not what examiners are looking for. So examiners are looking for a nice use of the majority of the graph paper, so you can see more clearly what's going on. Note that the crosses have been put on. Okay, don't use little dots or smudges. Nice crosses, and where the lines are crossing, it should be the data point. So 0, 0 is our first one, 2, 1, 4, 2. We read across 4, for the 4, 2, we go 1, 2, 3, 4. And then we don't go up 2, we go up 4, because that scale is 1 for 2 little squares, 2 for 4 little squares. So you have to be careful when you're plotting that you're doing it correctly. Have a go yourself, see if you can plot up this graph using some of your own graph paper. Now we need to describe from the graph what is happening between 0 seconds and 6 seconds. So if we look back here, here's 0 seconds and 6 seconds. Well, we can see it's pretty much a straight line. So that means that the distance is increasing uniformly. It's really Important to use that word uniformly. That means constantly or the same. It's increasing, distance is increasing at a constant rate. Therefore, the velocity is constant. So, talk about the distance, what's happening to the distance, and talk about the velocity. Think about everything that the graph could possibly be showing. What is happening between 12 seconds and 16 seconds? Well, here's 12 seconds, and here's 16 seconds. So if we have a look at the line, at 12 seconds, we are at this point, and at 16 seconds, we're at this point. So it's really where this graph is flat here. So the distance is not changing. It's not increasing, it's not decreasing. So the buoy is stationary. The distance is not changing. What is happening between 18 seconds to 28 seconds? Oh, by the way, here you could also write velocity is 0. Velocity is 0 here. It's not moving. What is happening between 18 seconds to 28 seconds? Well, 18 seconds this is 18 seconds here, so we see where it is on the line. So it's this point here, that's 18 seconds, and 28 seconds is at the end of the data. So what's happening along this part? Well, again, it's a straight line, but what's happening to the distance is decreasing. So the buoy is going backwards, right? So there's less distance being covered over time. It's really strange. So what could possibly be going on is the buoy is going backwards and returns to the start. Velocity is uniform from 16 seconds to 20 seconds. It becomes less at 20 seconds. So we've got a uniform velocity here, and then we've got another uniform velocity which is less than this velocity. We can see that by the steepness or the gradient of the line. The gradient of the line is less steep here, so the velocity is less. Calculate from your graph the average speed from 0 seconds to 6 seconds. So in order to do that, from 0 to 6, we need the gradient of this line. So it's the rise divided by the run. Some people like to remember it like that, or some people like to think, oh, it's the change in the y-axis divided by the change in the x-axis in that given time. This also relates to, if we have a look at the change in the y-axis divided by the change in the x-axis, in this graph, that is the distance divided by the time. The change in the y-axis is the distance, and the change in the x-axis is the time. So this gives us 3 divided by 6. That gives us 0.5 meters per second. What is the distance travelled after 21 seconds? So the distance travelled from a speed-time graph is found by the area under the curve. So after 21 seconds, that's here, that's 21 seconds down to here, we need to know the area under this line, right? And that area is the area of a triangle. So it's a half base times the height. Or you can just write 15 plus 8. Why has he done that? Why has the student done that? Well, after 21 seconds, okay, 21 to 28, that's 7 seconds, isn't it? 21 to 28. So 21 to 28 is 7 seconds. And the height of this triangle is here. This is at 21, read across. So we go 6, 7. So a half base times the height is a half times 7 times 7. 7 times 7 is 49, and half of that we get 23. Okay, so 23 meters.